So, what are the observational uncertainties? We have already mentioned it several times as well. And anything you want to do in terms of predictions at any time scale versus projections into the future as well, you need what is called process understanding, and that can translate into predictive understanding, model improvements, better projections, more reliable projections, and so on. We saw this figure before, the historical observations from different data sources here. The shorter one is, of course, the satellite data TRMM, which only started in 1997. Others mix various kinds of satellites, in situ observations, gauges, and so on. And I had mentioned the issues here. For example, some remain in the positive realm and some go negative. This one, IMD, remains negative. The others one have gone to positive, the so-called monsoon recovery. I didn't stress the trends in the previous time I showed this figure, but here we are. In the negative trend part, the various colors here correspond to trends going from minus 0.18 millimeter per day versus, sorry, the trends should be in. The numbers in the box denote significant trends at 95% confidence, again millimeters per day. So you can just note, if you don't want to remember, just remember the range of these trends here. Minus 0.18, which is quite high, compared to minus 0.10 in the mean of these, for example. And if you look at the recovery part here, one of them, the crew data, which comes from the East Anglia, I think, that shows claims a trend, positive trend of 1.34 millimeters per day, whereas others are as little as half of it or even less than that. One of them, the IMD rainfall, doesn't even show much of a positive trend. It does show some recovery, but compared to the others, it's much smaller. So this is one example, but you can also look at the trends in various spatial aggregations. So these are long-term trends in millimeters per day per year, so that's the same here as well. In monsoon seasonal rainfall, June, July, August for 1951 to 2004, for multiple observational data sets with data availability since the 1950s. We are looking at subregions here. The data sources, IMD has two products, 1 degree by 1 degree product, and a reprocessed 0.25 by 0.25 degrees. Aphrodite is another data that has a resolution similar, and the IITM, the Indian Institute of Tropical Meteorology, does regional averages as well. And you can again see all India rainfall, IMD, two products have very different trends. The 1 degree by 1 degree says minus 0.89 millimeter per day millimeter per day per year, and the other one says 0. Aphrodite has even higher, minus 1.11, and the IITM regional averages dataset produces minus 0.91. How do you deal with these, and how do you place these in the context of model evaluation and future projections? Because if models are not doing well, then the data cannot constrain the models. Then you're not always sure whether models are doing something wrong and what they are doing wrong, whether they are doing the microphysics wrong, the dynamic responses wrong, or the thermodynamic responses wrong, which obviously has even a bigger impact on extremes, which are even less observed than these rain gauges data as an average. Okay, so other regions, West Central, again large differences. If you look at the IMD product here and the IITM product, that's remarkably different. Peninsular India, only one Aphrodite shows a seriously negative trend, whereas the others show no trend. Northwest, the uncertainty range is the range between them is smaller. Central Northeast, IMD data says a positive trend of 1.12. The others show no trend. Northeast, you can see there are both large positive numbers in terms of millimeters per day per year. So obviously you have to find other evidences which support this, either in terms of vegetation, groundwater recharge, whatever else you can find. Okay. Northeast hilly regions, IMD data size minus 11.9. IMD, the high resolution product says minus 7.01, and IITM doesn't have data for that region, but the satellites also have trouble estimating rainfall rates over hilly regions. That's even a further limitation. Jammu and Kashmir, again, IMD data says positive 1.83, which is massive. Aphrodite data says minus 0.72, which is a significantly negative trend. So this is a serious challenge of doing rainfall process understanding or predictions as well. This is the figure. This figure is showing comparison of the climatological patterns of different rainfall characteristics from 5 data sets. I won't read what they are, but the climatology is calculated over this period of 1981 to 2007. Depiction of political boundaries in these maps may not be authoritative accurate because of all these geopolitical issues here. The maps can look different in different versions that you can find. But you can see the seasonal totals in different products. Again, differences are not small. This is the dry day frequencies, remarkably large differences in some places. This is the 95th percentile total probable profile. Oops, sorry. I can't even read properly here. 5th percentile and total 95th percentile, whatever. But the main point is that they are all different. Look at the difference here in the 5th percentile. This one is showing a very high positive pattern, whereas the others have hardly any signal. Okay, so whether these are data reporting issues, data gathering issues, interpolating issues, missing data, and so on, are not always easy to figure out. Okay, here we are looking at the same as the previous figure, but for linear trends over 1981 to 2013. Gray dots indicate significance of trends at the 5% level or the 95% confidence, and depiction of political boundaries, again, you have to be careful about. So here are the seasonal totals, dry day frequencies, 95th percentile, total precipitation greater than 95th percentile, which I couldn't read here, sorry. And this is the 5th percentile, and total precipitation less than the 5th percentile, so the low rain rates. Again, the idea of having such high frequency small scale trends and variabilities in rainfall is always something to worry about, because even averaged over such long periods and trends over such long periods, what dynamics is needed to produce such small scale trends which are positive and negative next to each other? What are the processes that would be involved in producing negative rainfall trend over this region and very high positive trend right next to it? So this is something that just process wise has to be understood. So there is convective available potential energy as an instability being generated, for example, and rainfall happens, moisture supply happens, but how do you get such different rainfall rates and rainfall trends over a long time between such adjacent regions? These are not easy questions. You can see also here the dry day frequencies also can have such high spatial patterns. In the topography it can make different, it can probably is more intuitive in terms of the mountain ranges producing very local responses, but when you go away from the topography and look at plain regions, how can you generate such high spatial variability and trends in rainfall? This is something that is needs to be understood as well, and if the models are not able to do it, or if the models don't have the resolution to capture those scales, then obviously we have a long way to go in terms of understanding the processes. Okay, but high resolution regional models are often used, and there are roles of land use change, agricultural land conversion, irrigation, deforestation, aerosols, of course, urbanization, and so on are all invoked as drivers of such local precipitation changes, even in extremes, not just in mean and variability and trend, but also in terms of the extremes. Okay, precipitation is always going to be a problem. You can think of it as, again, I've said this before, a popcorn kettle which is being warmed. The temperature is fairly uniform, but the kernels of popcorn will just pop in random places, even though the temperature gradient is probably immeasurable. So tiny factors contribute to these small decorrelation scales of precipitation. Precipitation is very much a local, especially tropical convection, is a very small scale microphysical process where feedbacks of vertical motion with the dynamics can drive extremes and very local scale changes. So this is a big challenge that has to be faced even in terms of future projections or understanding past data with all these data limitations and data uncertainties. Okay.